Today we will learn about gearing heavy-duty trucks in today's challenging environment. The EPA continually advances the trucking industry in its efforts to reduce the carbon footprint created by the transportation sector. To meet the steep regulations, equipment manufacturers are engineering to embrace the goals established by the federal government. These advances have presented a marked change in how engines perform today, as opposed to in years past. So, if you're interested in replacing a vehicle today, then you need to understand how to gear current engines to achieve your productivity and profit goals. For purposes of this instruction we are using Z-Factor Consultation's Z Gear Comparison tool to assist with visualization of the impacts. Put simply, this product is an Excel worksheet that allows users to input 3 different gearing scenarios and calculate an RPM, where the engine will operate for the given speed. Next the user can compare the calculated result against the engine manufacturer's recommendation to see how it aligns with the goals and objectives of the owner. In this example I have entered 3 ratios, keeping all data about speed, tires, and transmission top gear the same. This method allows me to isolate and study the relative outcome of the selected gearing, before the vehicle is built. The top left-hand box, Result 1, includes the ratio which the customer previously used on their 2013 trucks, viewed here for an EPA 17 engine. Result 2 is a suggested improvement for consideration. Result 3 is a more aggressive solution. For those of you who are unfamiliar with the torque curve, this is the graph that displays in the right-hand box. It is unique to the engine selected. In this case an X15 500 horsepower engine from the Cummins Productivity Series. This engine is capable of producing 1850 foot-pounds of torque. RPMs of the engine are defined across the bottom of the graph. The brown arc represents the torque available at each RPM. The colored bands in the display are defined in the engine manufacturer limits presented below the graph. The sequence is always the same: fuel economy is to the left, balance is in the middle, and performance to the right on the graph. The further to the left you go within the entire band range at peak torque, the less fuel the engine will consume. Peak torque is the flat portion of the curve. If you were able to draw a line on the torque curve at the Result 1 calculated RPM, you would see something similar to the blue dashed line in the display area of the calculator. Compare the calculated result in color band to the engine manufacturer's definition to see which optimization profile this gearing falls under. In this case, Result 1 is at the end of balance, near performance. This result is within the engine manufacturer's recommended operating band, but falls quite beyond the defined fuel economy range. If you were able to draw a line at the Result 2 RPM, you would see something similar to the orange dashed line in the display area of the calculator. As compared to the engine manufacturer's definition, this ratio would fall to the left of Result 1. It's close to balance, at the end of the fuel economy gearing recommendation. If the customer drives the vehicle at 68 miles per hour, they can expect that this ratio would result in better fuel economy than their existing ratio would with an EPA 17 engine. The calculated RPM for Result 3 is displayed here as the green dashed line. You will see that this result falls in the middle of the fuel economy RPM range. The solution is not overly aggressive, since peak torque for the engine occurs well before. For this engine 1850 torque is reached around 950 RPM. Additionally, torque, or ability to pull the load, does not drop off until just over 1350 RPM. That being said, this result is very satisfactory from a driver's standpoint. Here is a comparison of all 3 gearing results combined. Keep in mind the engine selected, it's a vocational series. The customer may not be looking for maximum fuel economy in their application, potentially making Result 2 more attractive. If fuel economy is paramount, you might want to change to an efficiency series engine to see the result of your gearing scenarios on that torque curve. This engine was built with an extreme focus on efficiency in line haul and tractor applications. When changing the engine to an efficiency series, you find that the torque curve looks nearly indistinguishable compared to a productivity series engine of the same specification. The RPM bands also are identical. Note both have peak torque at 950 RPM. This is due to matching characteristics between these families, and changes only when you get to 565 horsepower in a productivity series engine. With the high horsepower engines in this series, torque distribution is completely different. Here the 565 horsepower engine is shown for comparison. See that peak torque occurs at 1200 RPM and the recommendation ranges also differ. You cannot use the same ratio from a 500 horsepower 1850 torque productivity engine. The solutions are unique, and the solution dictates the performance. Additionally, you would never want to specify 565 plus horsepower in a productivity series engine for an application where fuel economy was the greatest objective of the customer. Lastly, we will look at a similarly rated engine in the performance series. Cummins defines this family as correct for line haul and heavy haul applications. The gearing comparison inputs are the same, but notice where they fall on the torque curve. Both the curve shape and the recommended operating RPMs are different for this engine family. Result 3 is no longer a recommended result. Result 2 comes close to the fuel economy recommendation, and Result 1 falls under the definition of balance. However, Result 1 is incapable of achieving 1850 torque. At geared speed the driver will have 1,700 foot-pounds of torque. This may not be an issue, but is worth discussing with the future owner. Perhaps your customer is happier with the performance of a 1,650 foot-pound torque engine based upon the comparison of the two ratings. Are 1,650 torque engines lower priced? Can you save money on clutch and transmission? This could be a benefit. You cannot erase the perception of your product once a poorly specified vehicle gets into the hands of the customer. These are conversations you will need to have with your clients. Prepare several scenarios and print out those documents. Share them with the future owner, and let them choose what they want. Gearing is nowhere near as simple as it was in the past, and understanding the impact of choices, as opposed to relying on history, will define your success. Also, it's impressive. We hope you've enjoyed this tutorial. Remember to visit www.zfactorconnect.com to use the calculator yourself. Let us know if you need assistance. We appreciate you taking time to make things better for you and your customer. Gary and Cindy.